Right now, somewhere in the middle of the Pacific Ocean, a steel engine taller than a 4-story building has been running continuously for weeks, not hours, not days, weeks. While you switch off your car every time you stop for coffee, the world's largest cargo ships almost never shut down their engines, not even when they're standing completely still. At first, that sounds like an enormous waste of fuel. Why would anyone burn thousands of dollars worth of fuel without moving a single meter? The answer completely changes the way you think about ships, because out here, silence is far more expensive than the roar of the engine. Today we're going inside the largest marine engines ever built to discover why turning one off in the middle of the ocean could cost millions of dollars, destroy a machine worth several million, and, in the worst case, cost lives. By the end of this video, you'll understand why captains follow one simple rule. Once the journey begins, the engine never sleeps. Every day, more than 60 large commercial ships cross the world's oceans. Together, they transport over 80% of global trade, everything from smartphones to cars to the coffee you drank this morning. Has probably spent weeks aboard one of these floating giants. And every one of them depends on a single machine, its heart. Hidden deep below the deck, inside a gigantic steel engine room. That's where the real story begins. Unlike your car, a cargo ship doesn't have a backup engine waiting in case something goes wrong. There are backup pumps, backup generators, backup systems for almost everything. But there's only one main engine. If it stops, the ship loses the only force capable of moving tens of thousands of tons of steel across the ocean, and restarting it is far more complicated than anyone imagines. Because this isn't just an engine, it's one of the most extraordinary machines ever built by humans, and everything about it operates on an entirely different scale. To understand why ships almost never shut down their engines, you first have to meet the machine itself. Because calling it an engine doesn't really do it justice. Step inside the engine room of a modern cargo ship, and it feels less like a mechanical compartment and more like an industrial building. Steel platforms stretch across multiple levels. Metal staircases climb several stories high. Pipes carrying fuel, oil, steam, and cooling water surround you in every direction. And standing at the center is the largest diesel engine on Earth. Forget everything you know about car engines. This machine operates on a completely different scale. Each cylinder is so enormous, a fully grown adult can stand inside it. Marine engineers literally climb into the engine during maintenance. Some engines have 6 cylinders, others have 8. The largest container ships use engines with up to 14 massive cylinders. Each piston weighs several tons. The crankshaft alone can weigh hundreds of tons. The largest marine engine ever built weighs over 2.3 tons and produces more than 107 horsepower, enough power to move an entire floating city across an ocean. Yet despite that incredible output, it turns at only about 100 revolutions per minute. Your car idling at a traffic light spins several times faster. Because these engines are not designed for speed, they are designed for one thing: relentless torque. Day after day, week after week, without stopping. There is another misconception many people have. This giant engine does not generate the ship's electricity. That is the job of several smaller auxiliary diesel generators. Lights, navigation systems, cargo cranes, air conditioning, communications. Everything electrical is powered separately. The main engine has only one responsibility: turning one enormous propeller, nothing else. And despite its size, this machine achieves something almost unbelievable. It converts more than half of the fuel's energy into useful movement. Over 50% thermal efficiency. A typical car engine reaches around 30%. That makes this the most efficient combustion engine ever created, an engineering masterpiece. But every masterpiece has one weakness: it has to eat. And what it consumes looks nothing like the diesel you pump into your car. Because the fuel that keeps this steel heart alive is almost solid. And that is where the real problem begins. The biggest engine on Earth runs on one of the cheapest and dirtiest fuels ever used. Not gasoline, not diesel. Something far heavier, something that, at room temperature, barely flows at all. It is called heavy fuel oil. The thick, black residue left behind after almost every valuable petroleum product has already been refined. Imagine freshly laid asphalt or warm tar. That is what this fuel looks like. At around 15 degrees Celsius, it is so thick it can barely move through a pipe. In fact, if you poured it into your car's fuel tank, it wouldn't even reach the engine. Yet every day, the world's largest ships burn thousands of tons of it. So how is that even possible? The answer is heat. Everything starts inside the ship's storage tanks. Even here, the fuel is already being warmed, just enough to make it slowly flow through the first pipes. From there, it moves into settling tanks, where water and heavy contaminants are separated from the fuel. Then it passes through purifiers spinning at incredible speeds. These centrifuges remove tiny particles that could destroy the engine's fuel injectors. Only after this cleaning process does the fuel begin its final transformation. Just before entering the engine, its temperature climbs to nearly 140 degrees Celsius. Only then does it become thin enough to be injected into the cylinders as a fine mist. Without that heat, combustion would be incomplete. Power would collapse, and the engine could suffer serious damage. The fuel doesn't simply need to be warm, it has to stay hot every second of every voyage. That's why the ship is filled with something most passengers never realize exists: steam. Kilometers of fuel pipes snake through the vessel. Almost every one of them is wrapped inside steam jackets, like an enormous floating hot water system. Every pipe, every pump, every filter must stay warm around the clock. Otherwise, the fuel begins thickening almost immediately. But here's the clever part. While the engine is running, keeping everything hot costs almost nothing. The hot exhaust gases leaving the engine are used to produce steam inside a waste heat boiler. Instead of throwing that heat away, the ship recycles it. That steam keeps the fuel hot. The hot fuel feeds the engine, and the engine creates more heat. It's a perfect circle, an incredibly efficient self-sustaining system, as long as the engine keeps running. Now imagine what happens the moment someone decides to shut it down. The exhaust heat disappears instantly. The waste heat boiler stops producing steam. Suddenly, the entire system depends on a much smaller auxiliary boiler. If that boiler can't keep up, the temperature inside hundreds of meters of fuel lines begins to fall. Slowly, silently, almost invisibly, the fuel becomes thicker, then heavier, then almost solid, inside pumps, inside filters, inside injectors, exactly where you need it to flow the most. And restarting the engine is no longer a matter of pressing a button. It becomes a race against a system that's literally turning to tar. Because reheating an engine this size is only the beginning of the problem. Getting it to come back to life is even harder. Keeping the fuel hot is only half the battle. Because even if every pipe is warm and every pump is working, there's still one enormous problem. How do you restart an engine weighing more than 2 tons? You don't turn a key, you don't press a button. And there certainly isn't an electric starter powerful enough to spin a crankshaft weighing hundreds of tons. These engines come to life in a completely different way. Instead of electricity, they use compressed air. Huge steel air receivers store air at pressures of around 30 bar. When the captain orders a start, special valves inject that compressed air directly into the cylinders. The pressure forces the pistons downward, one after another, cylinder after cylinder, until the massive crankshaft begins to rotate. Only then, when the engine reaches the required speed, is fuel injected into the cylinders. Combustion takes over. And the giant wakes up. It sounds simple, but there's one catch. The compressed air isn't unlimited. International maritime regulations require ships to carry enough stored air for a limited number of consecutive starts. For many large engines, that's just 12 attempts. Think of them as 12 chances, 12 bullets. If the engine refuses to start, every failed attempt consumes one of them. And unlike fuel, you can't refill those air tanks instantly. The compressors need time, sometimes a lot of time. Now imagine the worst possible scenario. You're more than 1 mile from the nearest port. The engine has been shut down. The fuel has cooled. The lubricating oil has thickened. You attempt a restart, nothing. Second attempt, nothing. Third, fourth, fifth. Every failed start drains another precious reserve of compressed air. And with each attempt, the odds get worse, because a cold engine is far harder to restart than a warm one. Eventually, if those air tanks run empty before the engine fires, the ship becomes exactly what every captain fears: a drifting island of steel, completely at the mercy of the wind, the waves, and the current. Waiting for a tugboat that could take days to arrive. Even a successful restart comes at a price. When an engine cools down, its massive steel components contract. Cylinder liners, pistons, cylinder heads, everything shrinks ever so slightly. Then, within moments of restarting, temperatures explode. Steel that was cold seconds earlier is suddenly exposed to combustion temperatures of hundreds of degrees. That rapid expansion creates enormous thermal stress. Tiny microscopic cracks begin to form inside the metal, invisible at first, but over years, they grow. Every unnecessary shutdown, every unnecessary restart, quietly shortens the life of one of the most expensive machines on Earth. Replacing just a single cylinder liner can cost tens of thousands of dollars and keep a ship out of service for days. That's why engineers avoid cold starts whenever they possibly can, because the cheapest restart is the one you never have to perform. But mechanical wear isn't what keeps ship owners awake at night. There's something even more expensive than damaging the engine: losing time. And in global shipping, every single hour has a price tag, a very large one. For a shipping company, an engine isn't just a machine, it's time. And in global shipping, time is money, a lot of money. A large cargo ship isn't simply owned and operated. Many are chartered by the day. Every extra hour at sea, every delay entering a port, every missed unloading slot costs real money. A medium-sized bulk carrier can cost tens of thousands of dollars per day to operate. The largest container ships, even more. Their schedules are planned weeks in advance. At the destination, a berth has already been reserved. Dock workers are waiting. Cargo cranes are scheduled. Thousands of containers are already assigned to trucks and trains. If one ship arrives late, everything behind it begins to. One delay quickly becomes dozens, sometimes hundreds. The world saw just how fragile that system is in March 2021. When the container ship Ever Given became wedged across the Suez Canal, global trade almost stopped. For 6 days, hundreds of ships waited on both sides of the canal. Factories ran short of parts. Retailers waited for products. Supply chains across the world slowed down. The blockage disrupted billions of dollars worth of trade every single day, all because one ship couldn't move. For ship owners, that was a reminder of one simple truth: a stopped ship is an incredibly expensive ship. But money isn't the biggest reason captains hate shutting down their engines. Safety is. Because out in the ocean, your engine isn't just propulsion, it's control. Imagine standing on the bridge during a violent storm. Towering waves crash across the bow. The wind is pushing thousands of tons of steel sideways. As long as the propeller is turning, the captain can keep the ship pointing directly into the waves. That's the safest position. The hull cuts through the sea. The vessel remains stable. But the moment the engine stops, everything changes. The ship begins losing speed. The rudder becomes less effective. The wind and the waves slowly take control. Instead of facing the sea, the ship can begin turning sideways. And that's exactly where things become dangerous. A massive wave striking the side of a powerless ship can generate forces the vessel was never designed to absorb. In extreme conditions, control can disappear in minutes. That isn't just theory. It almost became one of the worst maritime disasters of modern times. On March 23, 2019, the cruise ship Viking Sky was sailing along the coast of Norway during severe weather. More than 1.3 thousand people were on board. Powerful waves caused the lubricating oil inside the engine system to violently. Oil pressure dropped below the safety limit. The protection system did exactly what it was designed to do. It shut down the engines automatically. All of them. Suddenly, a ship carrying 1.373 passengers and crew had almost no propulsion, almost no steering, and a rocky coastline getting closer with every passing minute. Inside the ship, furniture slid across the floors, tables overturned, passengers struggled to stand. Many believed the ship was about to capsize. The captain issued a mayday. Norwegian rescue helicopters launched immediately. One by one, nearly 500 people were airlifted from the deck while the ship rolled violently beneath them. It took almost 40 minutes before enough engine power was restored to regain control. Investigators later concluded the ship came dangerously close to running aground. Just one hull length separated it from disaster. It was a powerful reminder that, at sea, an engine isn't just a machine. It's the difference between control and survival. So if shutting down the engine is almost never worth the risk, is there ever a time when these giant steel hearts are actually allowed to rest? The answer is yes, but only under very specific conditions. So, do these giant engines ever get to rest? Yes, but only when 3 conditions are met. The ship is close to shore, there's enough time, and the sea is safe. Only then can the heart finally stop beating. When a cargo ship arrives in port for a long loading or unloading operation, the main engine is shut down in a carefully planned sequence. There's no rush, no pressure, no storm. The auxiliary engines continue generating electricity for the entire vessel. Lights remain on. Cargo cranes keep working. Navigation systems stay powered. Life aboard the ship continues almost exactly as before. Meanwhile, the auxiliary boiler keeps heating the heavy fuel oil. The fuel never has the chance to cool completely. Everything is maintained, ready for the next voyage. This is also when engineers perform the maintenance that would be impossible in the middle of the ocean. Cylinder liners are replaced, fuel injectors are serviced, pumps are rebuilt, thousands of individual components are inspected. Some repairs can take several days, others several weeks, but none of them are ever planned hundreds of miles from land. Because once the ship leaves port again, everything changes. Before departure, the entire starting sequence begins in reverse. The auxiliary boiler heats the fuel, steam warms the pipelines, lubricating oil reaches the correct temperature, the compressed air receivers are fully recharged. Every system is checked, twice. Only when every parameter is exactly where it should be does the chief engineer authorize the restart. Because out at sea, there are no second chances. For generations, sailors have had an expression for this moment. A ship is said to be cold iron. It comes from the age of steam, when a vessel remained in port long enough for the boilers to go completely cold. The steel engine finally cooled to the touch. Only then could it truly rest. Out in the ocean, that almost never happens. And yet, the shipping industry is changing. For decades, These giants ran almost exclusively on heavy fuel oil, cheap, dirty, and incredibly difficult to handle. But environmental regulations are forcing a new generation of engines to emerge. In recent years, some of the world's largest container ships have begun operating on methanol, a cleaner fuel that dramatically reduces emissions. Others are being designed to run on ammonia or even multiple fuels, depending on availability. Entire fleets are being rebuilt, engines are being replaced. Technology is evolving faster than ever before. But despite all these changes, one thing hasn't changed. Not yet. Whether the ship burns heavy fuel oil, methanol, or tomorrow's fuel, the rule remains exactly the same. In the middle of the ocean, the engine keeps running, because this was never just about saving fuel. It was about protecting a machine worth millions of dollars, protecting cargo worth hundreds of millions, and most importantly, protecting the people on board. Sometimes, the most expensive decision is the one that looks cheapest. Turning off the engine might seem like common sense, but in the middle of the ocean, it's one of the most dangerous choices a captain could make. Right now, as you're watching this video, thousands of cargo ships are crossing the oceans, carrying more than 80% of everything traded on Earth. Your phone, your clothes, your coffee, your furniture. At some point, almost all of them traveled aboard one of these ships, powered by an engine that never slept, a steel heart beating day and night across thousands of miles of ocean. Not because engineers forgot how to switch it off, but because keeping it alive is the safest, the smartest, and ultimately the cheapest decision of all. If you enjoyed discovering the hidden engineering behind one of the world's most incredible machines, you're in the right place. Here on Source Code, we reveal how the systems that power our world really work, from giant factories and engineering marvels to the technology hidden beneath everyday life. If you don't want to miss the next journey, subscribe, turn on notifications, and join us next time. Thanks for watching, and we'll see you in the next episode of Source Code.